All right. What we are going to do in this lesson is look at a different type of angle within a circle. Remember, last lesson you looked at central angles. Central angles have their vertex at the center. And remember, central angles have the same measure as its intercepted arc. What we are going to look at today is what we call an inscribed angle and identify its relationship with its intercepted arc. So if we take a look down here at our circle, we can draw in an inscribed angle. An inscribed angle has its vertex not at the center, like a central angle, but an inscribed angle has its vertex on the circle. On the circle. The intercepted arc is the portion of the circle that is in between the arms of that angle, okay? So our intercepted arc is that pink part of the circle. It's the arc between the rays of the angle. So what we're going to look at now is some examples of inscribed angles and their intercepted arcs, and we're going to look at the angle measures of the angles compared to the measure of the arc. So in the first example, the measure of the inscribed angle is 27 degrees. The measure of its intercepted arc is 54 degrees. In the second example, the measure of the inscribed angle is 50 degrees. The measure of the intercepted arc is 100 degrees. And finally, in a more general sense, the measure of the inscribed angle is x. The measure of the intercepted arc is 2x. So what we need to do is we need to generalize what we're seeing here between the inscribed angle and the intercepted arc. Hopefully you're seeing that the measure of the arc is twice the measure of the angle. The measure of the intercepted arc is twice the measure of its inscribed angle. And of course, you could look at this going the other way. You could say that the measure of the angle is half the measure of the arc. So either way you look at it, just in like these three examples, the measure of the angle, the inscribed angle, is half the measure of the intercepted arc. Number 3 says for us to draw another inscribed angle up here in number 1 that intersects the same arc AC. So what we're going to do, our endpoints of the angle are still going to be A and C, but the vertex of our angle is going to be on another part of the circle. Again, notice that the endpoints of the angle are on the same two places, A and C, but this time the vertex of our angle, let's call it D, is in a different place. So what we want to think about is what is the measure of angle ADC, the new angle that we just drew here. Well, if you notice, because it has the same endpoints as the first angle, it has the same intercepted arc. Because it has the same intercepted arc, this Sorry, we had a fire drill, and now I lost my train of thought. Okay, so because this angle has the same intercepted arc as this angle, the two angles will have the same measure. So the measure of angle ADC is also going to be 27 degrees. So that was question number 3. So now we have a couple of questions down here. I'll do the first couple with you, and then I'm going to have you do the last one in each group. So in the first one, you are given that the measure of the angle is 115 degrees. The measure of the arc is going to be twice that. So the measure of arc ZWX is going to be 230 degrees. We know that this is going to be a major arc because its measure is greater than 180 degrees. So make sure you're naming it with 3 letters. And the angle times 2 is the measure of the arc. In the next example, this time we're given that the measure of the arc is 100. So we are looking for the measure of angle N, my angle symbol, measure of angle NMP. If the arc is 100, then the angle will be half that, which is 50 degrees. All right, I would like you to do this last one on your own. You should have that the measure of arc STQ is 180 degrees. Notice that the measure of your angle is 90 degrees, so times 2 is 180. So now we're going to look at some examples where you have the two inscribed angles with the same intercepted arc. So notice these two angles have the same intercepted arc. So because they have the same intercepted arc, the angles have to be congruent. So if we're looking for the measure of angle F, the measure of angle F has to be the same as the measure of angle E, which is 75 degrees, because they have the same intercepted arc. On this one, we're finding the value of x. So here's our first intercepted arc. Notice endpoints are at E, and that's an H. The second angle is right here. It also has endpoints at E and H. Again, those two angles have the same intercepted arc, so they have to be the same measure. I'm going to go ahead and do the first part with you. Let's look at first finding x. So angle x is right here. It has endpoints Q and R. So I'm looking for the other angle that has endpoints Q and R. That would be angle P, goes through Q and R. So x is the same as 45. And then you could do a similar type of thing. There's angle Y, endpoints P and S. The other angle with endpoints P and S is the angle with 40 degrees. So Y is 40 degrees. The next thing that the last thing that we are going to talk about in this lesson is what we call an inscribed polygon. An inscribed polygon is just a polygon where all of the vertices are on the circle. The easiest way to draw an inscribed polygon, I just usually make a few, let's say it's a pentagon, so I'll have 5 vertices somewhere along the circle, and then I just connect those with segments. It's not the prettiest picture, but all of my vertices are on the circle. We say that the circle is circumscribed about the polygon. So circum just means circle or around. Inscribe means to write. So the circle is written around the polygon is all that means. So if you're told that the circle is circumscribed about the polygon, then that means the polygon is inscribed. Okay? We have two theorems about inscribed polygons that we will talk about. The first one says that if you have a right triangle inscribed in a circle, which you can see in the picture you have, then the hypotenuse is the diameter. If you have a right triangle inscribed in a circle, so notice that you have the endpoints on the circle. This is a right triangle. The hypotenuse of that right triangle has to be a diameter of the circle. And that converse is also true. So if you have a triangle inscribed in a circle where one side goes through the center, that has to be a right triangle. And finally, this is talking about quadrilaterals specifically, so anything with 4 sides. Okay, quadrilaterals can be inscribed if and only if the opposite angles are supplementary. If and only if the opposite angles are supplementary. Remember, that means they add up to 180 degrees. So in your picture, this would mean that F and D, so the measure of F plus D equals 180, and that would mean that the measure of E plus G also equals 180. Opposite angles are supplementary. All right, so if we use that last one, really is the one we'll use the most to solve some problems. We can look at the first one. Notice that all of the vertices are on the circle. That means it's inscribed. And it's a quadrilateral. So just like that last example, opposite angles are supplementary, meaning x plus 85 equals 180. If we subtract 85 from both sides, we get that x equals 95. And we can do the same thing for the other two opposite angles. The 80 plus the y must equal 180. Subtract 80 from both sides, and y equals 100. I would like you to stop the video and do the next example now. For this example, we should have that z equals 100 and y equals 60. All right, we have one last example to look at, and I'm going to do this one with you because this one includes a system of equations. So we've been reviewing just slightly systems of equations, but this time we actually have to write out the system ourselves. So again, we have a quadrilateral inscribed in a circle. The vertices are on the circle, so opposite angles are supplementary. Notice they already color code them for you. So let's look at the red ones first. We can say that 3x plus 3y equals 180. We're doing the same thing that we did in the last two examples. And then let's do it for the other two angles. So 5x plus 2y, those must also equal 180. So now we have a system of equations which we need to solve. Probably elimination is our best bet. We want to eliminate one of the variables. If we multiply the first equation by -5 and the second equation by 3, that will make this a -15 and this a +15, which would then cancel out. We'll distribute that -5 through. Make sure you also multiply it by the 180, and we'll distribute the 3 through. At this point, we can add our two equations and notice the x's drop out. Oh, I made a mistake. I just noticed. That should not be -6y. That should be I made two mistakes. Oh, I'm sorry. These are not correct either. Okay, let me back up. I apologize. Okay, so we distribute -5 throughout, so that's -15x. That should be -15y equals, that's -900. And then distribute the 3, that's 15x plus 6y equals, that's 540. I apologize. So now after we correctly distribute the -5 and the 3, now we can add our equations. We still get the x's to drop out, but now I have -9y equals -360. I can divide both sides by -9. And I get the y equals 40. So the measure of y is 40. To get our value of x, we can go back. I just always go back to the original first equation. I'm going to take that y and I'm going to plug it in. So 3x plus 3 times 40 equals 180, and solve. And we should be getting that x equals 20.